There is a planet in our solar system that no one takes seriously. It's the punchline of jokes, the one teachers rush past, the one documentaries barely mention. Between the drama of Mars and the majesty of Saturn's rings, Uranus drifts quietly in the background, pale, distant, almost forgotten. But Uranus may be the strangest world orbiting the Sun. It spins on its side. It has seasons that last decades. Its atmosphere hides violent storms beneath a calm blue surface. And deep inside, something doesn't make sense. For decades, scientists thought Uranus was simple, a quiet, frozen gas giant drifting in the dark. A cold, featureless sphere, a planet without personality, a frozen relic at the edge of the solar system. But recent discoveries suggest something far more mysterious. Its magnetic field is chaotic. Its interior structure may be completely different from what we believed. Its heat signature doesn't match the models. And its extreme tilt could be the scar of a catastrophic collision billions of years ago. Some astronomers now think Uranus might hold clues about how planetary systems form, how giant worlds evolve, and even how alien planets behave around distant stars. Uranus isn't boring, it's misunderstood, and the deeper we look, the stranger it becomes. Tonight, we're going to see why. For most of human history, Uranus did not exist. Not because it wasn't there, but because we couldn't see it clearly enough to recognize it for what it was. To the naked eye, Uranus is just barely visible under dark skies, a faint, unmoving point of light. Ancient astronomers recorded it several times, but they mistook it for a star. It didn't wander dramatically across the sky like Mars or Jupiter. It didn't blaze like Venus. It simply lingered. It blended in. And that was the first misunderstanding. In 1781, William Herschel observed the faint object through his telescope and noticed something unusual. It wasn't quite star-like. It had a tiny disk. It seemed to move slowly against the background stars. At first, he thought it might be a comet. It wasn't. For the first time in recorded history, humanity had discovered a new planet. Uranus was the first planet found with a telescope, expanding the known boundaries of the solar system overnight. Suddenly, the neat structure of 6 classical planets was broken. The solar system was bigger than we thought. But from the very beginning, Uranus didn't behave the way we expected. Even its orbit was strange. Precise measurements later revealed tiny deviations, subtle gravitational tugs that couldn't be explained by known planets. Those deviations eventually led to the discovery of Neptune. So, in a way, Uranus helped us find another world simply by not behaving properly. Already, it was hinting that it wasn't ordinary, but its true strangeness lies not in how it orbits the Sun, but how it spins. Most planets rotate like spinning tops. Their poles are roughly upright relative to their orbit. Earth tilts about 23 degrees. Mars tilts about 25 degrees. Even Saturn, with all its rings, tilts only about 27 degrees. Uranus tilts 98 degrees. It doesn't just lean, it lies on its side. Imagine Earth rolling around the Sun like a barrel instead of spinning like a globe. That's Uranus. Its north and south poles don't point up and down relative to its orbit. They point sideways. For nearly a quarter of its 84-year orbit, one pole faces almost directly toward the Sun, while the other is plunged into darkness. That means a single season on Uranus lasts about 21 Earth years, 21 years of continuous daylight, 21 years of continuous night, no sunrise, no sunset, just a slow, relentless shift in sunlight over decades. This extreme tilt changes everything about the planet's climate and atmospheric dynamics. When one hemisphere receives constant sunlight for decades, its atmosphere warms differently. Winds shift, cloud structures change, methane absorption varies, and then, as the planet continues its long orbit, the lighting flips. No other planet in our solar system behaves like this, and scientists believe this bizarre orientation likely came from violence. Early in the solar system's history, something enormous may have struck Uranus, a protoplanet perhaps twice the size of Earth. The impact could have knocked Uranus onto its side permanently. If that's true, Uranus is a survivor of catastrophic planetary trauma, and that trauma may still shape its interior today. But even without the tilt, Uranus defies expectations in another way: temperature. You would assume Uranus is frigid simply because it's far from the Sun, about 2.9 billion kilometers away on average. Sunlight there is weak, faint, barely more than a bright star compared to what Earth receives. And yes, Uranus is cold. The coldest atmospheric temperatures measured in the solar system were recorded there, around minus 224 degrees Celsius, colder than Neptune, colder than Pluto's average surface temperature in some measurements. But here's the mystery. Neptune, which is even farther from the Sun, radiates more internal heat than Uranus. Neptune emits more energy than it receives from sunlight. It glows slightly with leftover heat from its formation. Uranus does not. Uranus emits almost no excess internal heat. It's as if something inside it is muted, as if its internal furnace has shut down or is trapped. That's strange. Gas giants typically retain leftover heat from their formation for billions of years. Jupiter and Saturn radiate significant internal energy. Neptune does too. But Uranus is quiet. Why? Some models suggest the ancient impact that knocked Uranus sideways may have disrupted its internal convection, trapping heat beneath layers that prevent it from escaping. Others suggest its internal composition might be fundamentally different from what we think, which brings us to another misunderstanding. Uranus is often grouped with Jupiter and Saturn as a gas giant, but technically it belongs to a different category, an ice giant. That doesn't mean it's made of solid ice. Instead, its interior likely contains large amounts of water, ammonia, and methane ices, substances that behave very differently under extreme pressure. Beneath its pale blue atmosphere, Uranus probably has a thick mantle of superheated, high-pressure fluid mixtures. Water there doesn't behave like ocean water. Under immense pressure, it may form exotic states of matter. Some experiments suggest that deep inside Uranus, water molecules may break apart under pressure and form a strange phase known as superionic ice, where oxygen atoms form a crystalline lattice, while hydrogen ions flow freely through it like a liquid metal. If that's true, then deep inside Uranus, it may literally rain diamonds. Laboratory simulations of Uranus-like pressures have shown that methane molecules can break apart, freeing carbon atoms that compress into diamond structures. Those diamonds may then sink toward the planet's core, like sparkling hailstones falling through a dense ocean of fluid. Whether that happens in large quantities remains uncertain, but the possibility alone reveals how alien Uranus truly is. And then there is its magnetic field. Earth's magnetic field is relatively aligned with its rotation axis. So are Jupiter's and Saturn's. Uranus's magnetic field is tilted by about 59 degrees relative to its rotation axis, and it's offset from the planet's center. It doesn't originate neatly from the core like a bar magnet. Instead, it appears lopsided and chaotic. As Uranus rotates on its side, its magnetic field wobbles and twists unpredictably, creating an ever-changing magnetosphere that sweeps through space like a tilted lighthouse beam. If you were a spacecraft orbiting Uranus, you would experience wildly fluctuating radiation conditions as the magnetic field swings past. This was briefly observed by Voyager 2 when it flew past Uranus in 1986. The only spacecraft ever to visit the planet, and even that flyby was quick. We've never gone back. Everything we think we know about Uranus comes from distant telescopes and that single fleeting encounter, which is perhaps the biggest reason it's misunderstood. We have sent orbiters to Mars, multiple probes to Jupiter, orbiters and landers to Saturn and its moons, rovers to the moon, flybys of Pluto. But Uranus, one pass. For a planet so strange, so tilted, so internally mysterious, we've barely looked at it up close. And yet, Uranus may be the key to understanding something much larger. When astronomers observe exoplanets around distant stars, many of the most common types discovered are similar in size to Uranus and Neptune. Ice giants appear to be common in the galaxy. That means Uranus is not a cosmic oddity. It may represent one of the most typical kinds of planets in the universe. Understanding Uranus isn't just about solving a local mystery. It's about understanding planetary systems everywhere. But because it doesn't have dramatic rings like Saturn or colorful storms like Jupiter's Great Red Spot, at least not visibly, it has been labeled boring. A bland blue sphere, a quiet planet, a background world. Yet recent observations have shown that Uranus is not calm at all. Beneath its serene appearance, storms rage. Cloud systems form and dissipate. Winds reach speeds over 900 kilometers per hour. It's just that most of its features are subtle, invisible light. The methane in its atmosphere absorbs red wavelengths of sunlight, leaving the planet with its characteristic cyan blue color. That absorption also hides deeper atmospheric layers from view. To see Uranus clearly, you need to look in infrared wavelengths. When scientists do, the planet reveals complex banded structures, polar caps, and dynamic atmospheric patterns. It isn't blank, it's concealed. Uranus has spent centuries being underestimated, discovered late, observed briefly, categorized too quickly. But the more we study it, the more it challenges our assumptions about how planets should behave. A world knocked sideways by violence, a planet with muted internal heat, a magnetic field that refuses to align, an interior that may contain exotic states of matter. Uranus isn't the solar system's joke. It's one of its deepest mysteries, and we've only just begun to understand how strange it really is. If Uranus were only tilted, it would already be unusual, but its sideways rotation does far more than create long seasons. It fundamentally reshapes the way energy moves through the planet's atmosphere, and possibly even its interior. To understand why that matters, we have to imagine what sunlight does to a planet over time. On Earth, sunlight heats the equator more than the poles. That temperature difference drives global circulation patterns, trade winds, jet streams, ocean currents. The sun is the engine behind Earth's climate system. Now imagine removing sunrise and sunset for decades. On Uranus, when a pole tilts toward the sun, it can experience constant daylight for roughly 21 years. The opposite pole remains in darkness for the same amount of time. Then, as Uranus continues its slow orbit, the situation reverses. This isn't just a long summer. It's an extreme redistribution of solar energy that changes the entire thermal balance of the atmosphere. And yet, despite this radical lighting geometry, Uranus often appears surprisingly uniform in visible images, a nearly featureless blue sphere. For decades, that uniformity confused scientists. If one hemisphere receives sunlight continuously for years, shouldn't we see dramatic atmospheric contrasts, giant storm belts, temperature extremes? But the atmosphere of Uranus doesn't respond the way Earth's would. Part of the reason lies in the planet's immense size and atmospheric depth. Uranus's atmosphere is thick and layered, composed primarily of hydrogen and helium, with methane giving it that distinct cyan color. Methane absorbs red light efficiently, which is why Uranus appears blue. But that same methane also influences heat transport in ways we're still trying to understand. Beneath the visible cloud tops, temperatures and pressures increase rapidly. And deeper still, the atmosphere transitions into a dense, supercritical fluid mantle. Unlike Jupiter and Saturn, which have significant internal heat contributing to atmospheric turbulence, Uranus lacks strong internal convection. That means much of its atmospheric motion is driven primarily by solar heating. And yet, solar heating is extremely weak at that distance. Sunlight at Uranus is roughly 1/400th as intense as what Earth receives. So what drives its winds? Despite the faint sunlight and weak internal heat, Uranus hosts winds that can reach speeds of 900 kilometers per hour, nearly matching those on Neptune. This is one of the great paradoxes. A planet with little internal heat and weak solar input still manages to generate powerful atmospheric dynamics. Recent infrared observations from telescopes like Keck and the Hubble Space Telescope have revealed bright cloud features forming near the poles and mid-latitudes, especially as Uranus approaches equinox. At equinox, sunlight falls more evenly across the planet, and during these periods, atmospheric activity appears to intensify. Storm systems bloom, bright methane clouds rise to higher altitudes, bands and vortices become visible in infrared wavelengths. It's as if Uranus wakes up, and this awakening seems tied to the seasonal transition, when decades of continuous illumination end and redistribution begins. Some researchers believe that energy stored in the atmosphere during long periods of sunlight may be released during these transitional phases, triggering storms and turbulence. But here's the complication. Because Uranus' internal heat is so low, the atmosphere may be stratified in a way that suppresses vertical mixing. That means energy and material from deeper layers may struggle to rise to the surface. This stratification could also explain the strange behavior of Uranus' interior. Unlike Jupiter and Saturn, which have well-mixed interiors that transport heat outward, Uranus might have compositional layering that traps heat below. Imagine a thick mantle where materials of slightly different densities are stacked in layers. If those layers resist mixing, heat cannot escape efficiently. This concept, known as a stably stratified interior, is one of the leading explanations for Uranus's low heat emission. But we don't know for sure. Voyager 2's brief flyby provided limited gravitational data, but not enough to map the internal structure precisely. Without an orbiter mission, we're essentially guessing based on models. And that brings us to another aspect of Uranus that challenges our understanding: its rings. Saturn's rings are iconic, bright, broad, and easily visible. Uranus's rings are faint, narrow, and dark. They were discovered in 1977, not through direct imaging, but through a stellar occultation, when Uranus passed in front of a distant star and briefly dimmed its light multiple times before and after the planet itself blocked it. Those additional dips in brightness revealed narrow rings. These rings are composed mostly of dark, radiation process material, possibly organic compounds altered by exposure to charged particles. They're not bright ice like Saturn's rings. They're subtle, almost invisible, unless you know where to look. And they may be relatively young. Some studies suggest that Uranus's rings could have formed from the remnants of shattered moons, disrupted by tidal forces or collisions. In fact, the entire Uranian system, rings and moons, appears dynamically fragile. Uranus has 27 known moons, many named after characters from Shakespeare and Alexander Pope. Unlike Jupiter's and Saturn's large, geologically active moons, Uranus's moons are mostly icy bodies with cratered surfaces. But even here, there are surprises. Miranda, one of Uranus's smaller moons, has one of the strangest surfaces in the solar system. It looks patchwork, as if someone assembled it from different geological pieces, giant cliffs, enormous fault scarps, and chaotic terrain suggests that Miranda may have been shattered and reassembled by gravitational forces in the past. The cliffs on Miranda are among the tallest known in the solar system, some nearly 20 kilometers high. How does a small moon end up with such dramatic features? Some models suggest that tidal heating, generated by gravitational interactions, may have briefly melted parts of Miranda's interior, reshaping its surface before it cooled again. This raises a fascinating possibility. Even in the cold outer solar system, icy worlds can experience bursts of internal activity if gravitational conditions are right. And that leads back to Uranus itself. Because of its extreme axial tilt, Uranus's magnetosphere rotates in a bizarre fashion. The magnetic poles swing wildly through space as the planet spins on its side. This creates a magnetosphere that changes orientation dramatically over the course of a single rotation, about 17 hours. Charged particles trapped in this magnetosphere interact with the rings and moons in unusual ways. Auroras have been observed on Uranus, faint glows caused by charged particles striking the atmosphere. But they behave differently than Earth's auroras. They don't align neatly with the rotation axis. They wander. The geometry is complex, shifting, and asymmetric. This magnetic complexity may also influence how the solar wind interacts with Uranus. During Voyager 2's flyby, the spacecraft detected a magnetosphere that appeared compressed and twisted. If we had an orbiter studying Uranus for years instead of hours, we might uncover entirely new plasma physics phenomena unique to tilted ice giants. But we don't, at least not yet, which means Uranus remains one of the least explored major planets in the solar system. In recent years, planetary scientists have increasingly argued that a dedicated Uranus orbiter and probe mission should be a top priority, not just because Uranus is strange, but because ice giants are common. When we detect exoplanets around other stars, many fall into a mass range between Earth and Neptune. These so-called mini-Neptunes are abundant in the galaxy. Understanding Uranus's interior structure, atmospheric chemistry, and magnetic field could provide critical insights into how these distant worlds behave. In other words, Uranus is a template, a nearby laboratory for a planetary class that dominates the cosmos. And yet, for cultural reasons, it has often been treated as a punchline rather than a frontier. Its name, derived from the Greek sky god Uranus, has become a source of jokes in English-speaking cultures. That trivialization may seem harmless, but it contributes to the perception that Uranus is unimportant. It isn't. It may hold answers to questions about planetary formation, interior physics, and atmospheric chemistry that we cannot answer anywhere else. Why did Uranus experience a massive collision early in its history? Did that collision strip away internal heat? Did it reshape its internal layering permanently? How do extreme seasonal cycles influence atmospheric evolution over billions of years? Is diamond rain truly occurring deep within its mantle? How stable are its rings over long timescales? These aren't minor questions. They are fundamental to understanding how planets form and evolve. Uranus forces us to confront the limits of our assumptions. It looks calm, but it hides complexity. It seems cold, but its interior may be exotic. It appears quiet, but its magnetic field is chaotic. It seems distant, but it may represent one of the most common planetary types in the galaxy. The deeper we look, the more Uranus resists simplification. It refuses to be just another gas giant. It refuses to fit neatly into categories. And perhaps that is why it has been misunderstood for so long, because it does not behave the way we expect planets to behave. And when a world challenges expectations, it demands that we rethink what we thought we knew. If Uranus were only strange in its tilt and magnetic field, it would already be remarkable. But the deeper mystery lies beneath its clouds, in a place we have never directly observed. Because Uranus is not just sideways, it is structurally uncertain. We often speak confidently about planetary interiors, cores, mantles, atmospheres, as if they are clearly layered like diagrams in textbooks. But those diagrams are models. And in the case of Uranus, those models are filled with assumptions. Unlike Earth, we cannot drill into Uranus. Unlike Mars, we cannot land seismometers. Unlike Jupiter, we have not sent an orbiter to map its gravity field precisely. Everything we believe about Uranus's interior is inferred from mass, radius, gravitational measurements from Voyager 2, and equations of state under extreme pressure. And the equations may not tell the whole story. Based on current models, Uranus likely has a small rocky core at its center, perhaps about the size of Earth. Surrounding that core is a thick mantle composed of ices, water, ammonia, and methane in superheated, high-pressure states. But these are not frozen ices. Under pressures millions of times greater than Earth's atmosphere, these materials behave more like dense fluids or exotic plasmas. Water at those depths is not liquid as we know it. it may enter a phase called superionic water, where oxygen atoms form a crystalline structure while hydrogen ions move freely through it like a metallic fluid. In this state, water conducts electricity, and that changes everything, because magnetic fields are generated by moving conductive fluids. On Earth, our magnetic field comes from the motion of molten iron in the outer core. On Uranus, if superionic water exists, it may play a role in generating its strange, tilted magnetic field. But Uranus' magnetic field is not just tilted. It is offset, significantly displaced from the planet's center. That suggests the magnetic dynamo may not originate deep in the core, but higher up in the mantle. Imagine a dynamo operating not at the center of the planet, but in a shell closer to the surface. That could produce a lopsided magnetic field, chaotic, unstable, asymmetrical, and that is exactly what Voyager 2 observed. But here's where the mystery deepens. If Uranus has this thick mantle of superheated fluids, and if internal heat exists beneath it, why does so little of that heat escape into space? Jupiter radiates about twice as much energy as it receives from the Sun. Saturn does too. Neptune emits more than it absorbs. But Uranus radiates almost no excess heat. Its thermal emission is barely above the sunlight it receives. This makes Uranus uniquely thermally dead among giant planets. Some scientists suspect that the ancient collision that tipped Uranus onto its side may have fundamentally altered its internal structure. Perhaps the impact rearranged internal layers in such a way that heat became trapped. Perhaps compositional gradients prevent convection. If materials of slightly different densities are layered carefully, heat transport can become suppressed. That would explain why Uranus appears so cold compared to Neptune, despite being similar in size and composition. But this is still speculation. We lack the data to confirm these models, and without a dedicated mission, the mystery persists. Now consider the implications beyond our solar system. When astronomers search for exoplanets, they frequently find worlds in the size range between Earth and Neptune. These sub-Neptunes, or mini-Neptunes, appear to be extremely common. In fact, they may be the most common type of planet in the Milky Way. But we do not have a mini-Neptune close enough to study directly, except Uranus and Neptune. If we misunderstand Uranus, we may misunderstand thousands of exoplanets. For example, when we observe a distant planet's mass and radius, we estimate its density. From density, we infer composition. But if Uranus's internal structure is more complex than we think, if layering traps heat and alters density in unexpected ways, our interpretations of exoplanets could be flawed. Uranus might not just be misunderstood. It might be distorting our broader understanding of planetary science. And then there is the atmosphere. At first glance, Uranus looks bland, a smooth blue-green sphere. But that smoothness is deceptive. The methane in its upper atmosphere absorbs red light, giving Uranus its pale cyan color. Beneath that thin, visible layer lie multiple cloud decks composed of different compounds: high-altitude methane ice clouds, deeper hydrogen sulfide clouds, and even deeper layers where temperatures and pressures rise dramatically. Recent observations in infrared wavelengths have revealed storm activity near the poles and mid-latitudes. Bright cloud features appear and disappear. Polar caps form seasonally. Wind speeds vary with latitude, Uranus may look calm in visible light, but in infrared, it reveals dynamic complexity. Its winds, although strong, are not as violently turbulent as Neptune's, but they are still significant. And the seasonal cycle, driven by its extreme tilt, likely plays a major role in atmospheric evolution. When Uranus reached equinox in 2007, astronomers observed increased storm activity. As sunlight shifted more evenly across hemispheres, atmospheric patterns changed. This suggests that Uranus's long seasons may store and release energy slowly over decades. It is a world governed by patience. Changes unfold over timescales far longer than a human career, and that may be why we struggle to understand it. We are used to rapid change, storms forming in hours, seasons lasting months. On Uranus, seasons span decades. If you were born during Uranian summer at one pole, you might reach adulthood before seeing your first sunrise in that region. Time behaves differently there. And then there are the moons. The Uranian system contains 27 known moons, most of them relatively small and icy. But their orbital configuration is fragile. Computer simulations suggest that some of the inner moons may be on unstable orbits that could lead to collisions in the distant future. The rings and moons form a delicate gravitational ballet. Unlike Saturn's bright rings, Uranus's rings are narrow and dark. They are composed of radiation-processed material, possibly the debris of shattered moons. And because Uranus's magnetic field sweeps asymmetrically through space, the interaction between charged particles and ring particles may be unique among planets. Every aspect of Uranus seems slightly off-center. Its spin, its magnetic field, its heat emission, its internal layering, its seasonal cycle. Nothing about it is straightforward. And yet, for centuries, it was dismissed as uninteresting, perhaps because it doesn't shout its drama. Jupiter displays giant storms in bold bands. Saturn glows with luminous rings. Mars shows deserts and polar caps. Uranus whispers. Its mysteries are subtle. They require infrared cameras, gravity mapping, magnetometers, and patience. But in that subtlety lies depth. If we truly want to understand planetary evolution, we cannot ignore the quiet worlds. Sometimes the most misunderstood objects are the ones that don't advertise their complexity. Uranus challenges our intuition. It shows us that planetary behavior is not always symmetrical, not always energetic, not always obvious. A planet can be massive, tilted, layered, magnetically chaotic, thermally suppressed, and still appear serene from a distance. That serenity is an illusion, and illusions are dangerous in science because they encourage complacency. Uranus is not boring. It is incomplete in our understanding. And perhaps the most important lesson Uranus offers is this: the universe does not owe us simplicity. Planets do not conform to tidy categories. Some worlds defy classification. Some hide their turbulence beneath pale clouds. And some, like Uranus, wait quietly at the edge of the solar system, challenging us to look deeper, question assumptions, and rethink what we thought we knew about how planets are supposed to behave. If Uranus challenges our understanding of planetary interiors and magnetic fields, it challenges something even more fundamental as well: our assumptions about planetary formation itself. Because Uranus should not exist exactly the way it does. According to standard models of solar system formation, The giant planets formed from a rotating disk of gas and dust surrounding the young sun. In the outer regions of that disk, where temperatures were cold enough for water and other volatiles to freeze, solid cores could accumulate quickly. Once a core reached a certain mass, it would begin rapidly accreting hydrogen and helium gas from the surrounding nebula. This is how we believe Jupiter and Saturn formed. But Uranus and Neptune are different. They are often called ice giants, not because they are made of frozen ice, but because they contain a much higher proportion of heavier elements. Water, ammonia, methane, compared to hydrogen and helium. And that difference creates a problem. If Uranus formed in its current location, about 19 astronomical units from the Sun, there may not have been enough solid material in the protoplanetary disk to build a core quickly enough before the gas of the solar nebula dissipated. Gas disks around young stars don't last forever. They typically vanish within a few million years. To build Uranus in place, a core would have needed to grow fast, extremely fast, in a region of the disk that was relatively sparse. Some models suggest that Uranus and Neptune may have formed closer to the Sun, where solid material was more abundant, and later migrated outward due to gravitational interactions with other planets. This concept, planetary migration, has reshaped how we think about the solar system. In certain simulations, the giant planets once occupied a more compact configuration. Through gravitational resonances and orbital instabilities, they shifted positions. In some versions of these models, Uranus and Neptune even swapped places. If that sounds chaotic, it was. The early solar system was not a quiet clockwork of stable orbits. It was a violent gravitational battlefield. Planets scattered planetesimals. Resonances amplified eccentricities. Collisions were common. And in that environment, Uranus may have experienced more than just one dramatic event. We often focus on the single giant impact that likely tipped Uranus onto its side. But what if that wasn't the only collision? Some researchers have proposed that Uranus may have experienced multiple impacts, each altering its structure in subtle ways. One impact could tilt a planet. Another could strip away part of its gaseous envelope. Another could disrupt internal layering. The end result might be a world that doesn't fit neatly into theoretical expectations. That could explain why Uranus differs so dramatically from Neptune. At first glance, Uranus and Neptune appear like twins. Their masses are similar. Their radii are close. Their compositions are broadly comparable. Yet Neptune radiates significantly more internal heat than Uranus. Neptune's atmosphere is more dynamically active. Neptune's winds are faster. If they formed similarly, why are they so different today? One possibility is that Uranus's ancient collision fundamentally altered its internal heat transport, while Neptune avoided such a catastrophic impact. Another possibility is that Uranus formed in a slightly different region of the disk, leading to compositional differences that affect long-term thermal evolution. Or perhaps our models of heat transport in ice giant mantles are incomplete. Because once you reach pressures and temperatures inside Uranus, familiar physics begins to shift. Water under those conditions is not like ocean water. Ammonia is not like household ammonia. Methane does not behave like the gas in a laboratory. These substances enter exotic states, supercritical fluids, metallic phases, electrically conductive layers. Under such extreme pressures, chemistry becomes strange. Some laboratory experiments have even suggested that under Uranian conditions, methane could break apart, releasing carbon in the form of diamond rain. Imagine droplets of diamond forming deep within the mantle, falling through superheated fluid layers toward the core. It sounds like science fiction, but high-pressure physics suggests it may be possible. If such processes occur, they would alter internal structure, density distribution, and heat flow. But we cannot directly observe them. We infer them from experiments on Earth, from shock compression studies, from theoretical equations. Uranus is far enough away that sending probes is expensive and slow. Voyager 2 gave us a fleeting glimpse in 1986, and since then we have relied primarily on telescopes. It is astonishing, in a way. A planet nearly 4 times the diameter of Earth remains largely unexplored. Now consider another dimension of Uranus's misunderstanding: its public image. It has become a punchline. Its unusual name and distant position have made it a target for jokes rather than curiosity. The cultural framing subtly affects perception. Planets like Mars and Jupiter receive cinematic attention. They are portrayed as dramatic, majestic, central to grand narratives of exploration. Uranus rarely occupies that spotlight, and yet, scientifically, it may be more crucial than we realize because of exoplanets. When astronomers began discovering planets around other stars in the 1990s, they expected to find analogues to our solar system. Small rocky planets close in, gas giants farther out. Instead, they found hot Jupiters, super-Earths, and sub-Neptunes. And as the exoplanet catalogue grew, a pattern emerged. Planets roughly between 1 and 4 times Earth's radius are extremely common. Many of these worlds likely resemble scaled versions of Uranus or Neptune. Thick atmospheres over volatile, rich interiors. If we misunderstand Uranus, we misunderstand one of the most common planetary types in the galaxy. For example, when telescopes like Kepler measure a planet's transit, the dimming of starlight as a planet passes in front of its star, they can estimate the planet's size. When combined with mass measurements, we can calculate density. From density, we infer composition. But if Uranus teaches us anything, it's that internal layering and thermal history complicate density interpretations. 2 planets with identical mass and radius could have very different internal structures depending on formation history, collisions, and heat transport. Uranus may be the key to unlocking that ambiguity. It serves as a laboratory for understanding mini-Neptunes across the galaxy. Now, let's return to its tilt. Not just as a curiosity, but as a driver of climate evolution. With an axial tilt of about 98 degrees, Uranus essentially rolls around the Sun on its side. For much of its orbit, one pole points almost directly toward the Sun, while the other is in darkness. Over the course of 84 Earth years, the length of one Uranian year, sunlight slowly shifts from one hemisphere to the other. During solstice, a pole can experience decades of continuous daylight. At equinox, sunlight distributes more evenly across latitudes. Such extreme seasonal forcing likely creates unique atmospheric circulation patterns. Models suggest that as a pole transitions from prolonged darkness into sunlight, temperature gradients may trigger changes in cloud formation and wind patterns. The 2007 equinox provided a rare opportunity for observation, and indeed, astronomers detected increased storm activity. This implies that Uranus is not as meteorologically inactive as once thought. It may simply operate on timescales that challenge human patience. When your seasons last decades, you don't rush atmospheric adjustments. This long seasonal rhythm may also influence chemistry in the upper atmosphere. Photochemical reactions driven by ultraviolet sunlight could vary dramatically between prolonged darkness and extended daylight. That means atmospheric composition might fluctuate over decades. But again, without continuous monitoring, we lack detailed data. And that is the recurring theme with Uranus. We lack data. Our understanding is based on a single flyby. Imagine trying to understand Earth's climate from a brief spacecraft pass lasting a few hours. You might conclude Earth is calm if you happen to observe it on a mild day. You might miss hurricanes, polar vortices, El Niño cycles. That is essentially what we have done with Uranus. We glimpsed it once. We have filled in the rest with models, and models are only as good as the data that constrain them. There are proposals now for dedicated missions to Uranus, orbiters equipped with magnetometers, spectrometers, atmospheric probes. Such missions could map gravity fields in detail, revealing internal mass distribution. They could measure magnetic field evolution over time. They could drop probes into the atmosphere to analyze composition directly. That would transform our understanding, because Uranus is not just a curiosity. It is a missing piece in planetary science. It represents a category of planet that dominates the galaxy. It challenges formation models. It complicates thermal evolution theories. It reveals that planetary magnetic fields need not align with rotation axes. It suggests that collisions can permanently alter planetary destiny. And perhaps most importantly, it reminds us that familiarity is deceptive. Just because something appears quiet does not mean it is simple. Just because a planet lacks dramatic rings or colorful bands does not mean it lacks complexity. Uranus sits in the cold darkness, rotating sideways, radiating little heat, holding secrets about exotic states of matter deep within. It forces us to confront the limits of our knowledge. And in science, that is often where the most important discoveries begin. Not in the worlds we think we understand, but in the ones we quietly overlooked. If Uranus teaches us anything, it is that planetary science is often built on very little information stretched very far, and nowhere is that more true than in the case of its atmosphere. From Earth, Uranus looks almost featureless, a smooth, pale cyanosphere. For decades, astronomers described it as bland. Unlike Jupiter with its swirling bands and great red spot, or Saturn with its elegant rings and visible storms, Uranus seemed quiet, almost empty. But that impression is misleading. The reason Uranus appears smooth is not because nothing is happening. It is because much of what is happening is hidden. The planet's atmosphere is thick, deep, and layered. At the top, sunlight filters through haze made of hydrocarbons, complex molecules formed when ultraviolet radiation from the sun interacts with methane. That haze scatters blue and green light, giving Uranus its distinctive color. Beneath that upper haze layer lie clouds made of methane ice crystals. Even deeper, scientists suspect clouds of ammonia and hydrogen sulfide. And far below those layers, perhaps hundreds of kilometers down, temperatures and pressures increased dramatically, transitioning into exotic states of matter. The problem is that we cannot see very far down. Unlike Jupiter and Saturn, which radiate significant internal heat and drive strong convection, Uranus emits very little extra energy. That means less vertical motion in its upper atmosphere, fewer towering cloud tops, less dramatic banding. But that does not mean calm. In fact, when astronomers began observing Uranus in infrared wavelengths, and especially when it approached equinox in the early 2000s, they saw something surprising. Storms. Bright transient features erupted in the atmosphere. Some were as large as continents on Earth. Winds reached speeds of over 800 kilometers per hour, comparable to or even exceeding winds on Neptune. For a planet once labeled boring, Uranus was suddenly dynamic. The seasonal explanation seems obvious at first. Because Uranus is tilted on its side, its poles experience decades of continuous sunlight, followed by decades of darkness. When the seasons shift, dramatic changes in atmospheric heating occur. Regions that have been frozen in darkness for years suddenly receive sunlight. That uneven heating may destabilize atmospheric layers, triggering convection and storms. But here is where it becomes complicated. Unlike Earth, where seasonal temperature changes are relatively modest, Uranus's seasonal energy distribution is extreme. For years, one hemisphere absorbs most of the solar energy, while the other receives almost none. And yet, despite that imbalance, Uranus's atmosphere does not show extreme temperature differences between hemispheres. Why? One possibility is that the atmosphere is remarkably efficient at redistributing heat. Even without strong internal energy, horizontal winds may transport warmth across the planet. Another possibility is that the deep atmosphere responds slowly to seasonal changes. The thick layers of gas and exotic fluids may act as a thermal buffer, smoothing out extremes over time. And yet, when storms do appear, they can be intense. Observations from the Keck Observatory and the Hubble Space Telescope have captured bright storm systems that seem to erupt suddenly, persist for weeks or months, and then fade. These storms are not fully understood. Are they driven purely by seasonal sunlight changes? Are they triggered by internal processes deeper within the planet? Or are they evidence that Uranus's internal heat is not as negligible as we thought? There is also the question of wind structure. Uranus exhibits strong zonal winds, east-west flows that form jet streams. Measurements indicate that wind speeds vary by latitude, creating complex atmospheric circulation patterns. Near the equator, winds may move in one direction, while at higher latitudes, they move the opposite way. The planet's extreme tilt complicates modeling these patterns. Because the axis of rotation lies nearly in the orbital plane, sunlight distribution shifts dramatically over its 84-year orbit around the Sun. Each season lasts about 21 Earth years. Imagine winter lasting longer than your entire life. Imagine summer lasting decades. The atmospheric response to such prolonged seasonal extremes is something we have no direct analog for on Earth. And that is what makes Uranus such a valuable laboratory. It represents a type of planetary environment that is common in the universe, but rare in our direct experience. Beyond the visible atmosphere lies an even stranger region. Under the methane and ammonia clouds, pressure increases until hydrogen, normally a simple gas, begins to behave differently. On Jupiter and Saturn, hydrogen transitions into a metallic state under extreme pressure. On Uranus, the composition is different. There is likely a mixture of water, ammonia, and methane under immense pressure, forming what scientists sometimes call an icy mantle, though the word ice is misleading. At those pressures and temperatures, water does not behave like the ice in your freezer. It becomes superionic. In a superionic state, oxygen atoms form a lattice structure, while hydrogen ions move freely through it, like a liquid flowing through a solid framework. This exotic phase of matter was predicted theoretically and later recreated in laboratory experiments using powerful lasers. If superionic water exists inside Uranus, it could profoundly affect the planet's magnetic field and internal heat flow. It also suggests that Uranus is not just an ice giant in the simple sense of containing frozen volatiles. It is a planet with materials in states we rarely encounter, materials that blur the line between solid and liquid, between familiar and alien. Now consider what this means for exoplanets. Many exoplanets discovered by missions like Kepler fall into a size range similar to Uranus and Neptune. They are sometimes called sub-Neptunes or mini-Neptunes. If Uranus contains superionic layers, stratified compositions, and suppressed convection, then many of those distant worlds may as well. Understanding Uranus is therefore not just about solving one planetary mystery. It is about interpreting thousands of distant planets we cannot visit. And yet, despite its importance, Uranus remains largely unexplored. The single flyby by Voyager 2 in 1986 provided the bulk of our close-up data. That spacecraft captured images, measured magnetic fields, and analyzed the atmosphere during a brief encounter. But it did not orbit. It did not linger. It did not observe seasonal changes over time. Everything we have learned since then has come from telescopes on or near Earth. Imagine trying to understand Jupiter without Galileo's orbiter, or Saturn without Cassini. That is our situation with Uranus. We have glimpsed it, but we have not studied it deeply. One of the most compelling future missions proposed by planetary scientists is a Uranus orbiter and probe. Such a mission would enter orbit and remain there for years. It could release an atmospheric probe to measure composition directly, sampling methane, hydrogen, helium, and trace elements. It could map the gravitational field to infer internal structure. It could monitor storms across seasons. It could observe the magnetosphere over time. In short, it could transform Uranus from a neglected outlier into a well-understood world. But until that happens, we rely on models, and models depend on assumptions. Some of those assumptions may be wrong. For example, for decades, scientists assumed Uranus was nearly inert internally. That assumption shaped atmospheric models and interior calculations. But if the suppressed heat emission is due to layered convection rather than a lack of heat production, then Uranus may contain more internal energy than we think, just trapped differently. Similarly, if its unusual magnetic field is tied to superionic layers, then our understanding of planetary dynamos must expand beyond the Earth-like model. Each new observation chips away at old simplifications, and gradually, the image of Uranus shifts, not from boring to exciting, but from simple to complex. It is a world defined not by spectacular visuals, but by subtle physical puzzles. And perhaps that is the deeper lesson. In planetary science, the most dramatic appearances are not always the most important clues. A pale blue disk in the outer darkness may hold more insight into planetary formation and evolution than the most photogenic gas giant. Uranus forces us to slow down, to look beyond aesthetics, to value data over spectacle. It is a reminder that scientific importance is not measured by brightness or popularity. It is measured by the depth of unanswered questions. And Uranus has many. Its atmosphere hides storms that challenge our expectations. Its interior may contain matter in exotic phases. Its seasons stretch across human lifetimes. Its magnetic field defies simple explanation, and its quiet appearance masks a dynamic and evolving world. If misunderstood, it is not because it lacks complexity. It is because complexity is often invisible at first glance. And Uranus, more than any other planet in our solar system, teaches us that first impressions can be deeply misleading. There is another reason Uranus continues to puzzle scientists, and it lies far beyond its atmosphere, its moons. At first glance, the moons of Uranus seem modest compared to the grand satellites of Jupiter or Saturn. There is no volcanic Io blazing with fire, no Europa with its hidden ocean, no Titan wrapped in a thick orange haze. Instead, Uranus is surrounded by a collection of icy worlds with names drawn from Shakespeare and Alexander Pope: Miranda, Ariel, Umbriel, Titania, and Oberon. But once again, appearances deceive, because the moons of Uranus tell a story of violence, freezing darkness, and perhaps even hidden activity. Start with Miranda. Miranda is one of the strangest moons in the solar system. It is small, only about 470 kilometers across, yet its surface looks as if it has been shattered and reassembled. Massive cliffs rise up to 20 kilometers high. Vast regions called corona form giant racetrack-shaped patterns. Some areas appear ancient and heavily cratered, while others look geologically younger. One towering cliff on Miranda, Verona Rupes, is the tallest known in the solar system. If you stood at its base and looked up, it would dwarf any mountain on Earth. How did such a small moon end up so fractured and chaotic? One explanation is tidal heating. In the past, Miranda may have been locked in orbital resonance with other moons. Gravitational interactions would have stretched and squeezed it repeatedly, heating its interior and triggering geological activity. Another possibility is even more dramatic: that Miranda was once destroyed by a massive impact and later reassembled from debris. That scenario would explain its patchwork appearance. Either way, Miranda suggests that Uranus's system was not always calm. Then there is Ariel. Ariel's surface is crisscrossed by long valleys and smooth plains that look younger than the surrounding terrain. Some scientists believe Ariel may once have had internal heat sufficient to drive cryovolcanism, eruptions of water or ammonia instead of molten rock. Imagine geysers spraying liquid beneath the icy crust billions of years ago. Even today, it is possible that some of Uranus's larger moons contain subsurface oceans. If tidal heating or radioactive decay kept interior layers warm enough, pockets of liquid water could persist beneath frozen surfaces. This possibility transforms Uranus's moons from frozen relics into potential habitats, at least in the distant past. But the most intriguing of the large moons is Titania. Titania is nearly half the size of our moon. It has vast canyons and a surface scarred by impacts. Some models suggest it may have retained enough internal heat to maintain a buried ocean beneath its crust. If true, Titania would join the growing list of ocean worlds in the outer solar system, alongside Europa, Enceladus, and perhaps even Pluto. And that realization reframes Uranus again, not as a lonely ice giant with inert satellites, but as the center of a system that may once have been geologically active and complex. Now consider the environment these moons endure. Because Uranus rotates on its side, its moons also experience extreme seasonal cycles. For decades, one hemisphere of the planet, and by extension its moons, faces constant sunlight. Then, for decades, it faces darkness. That prolonged exposure to sunlight and shadow affects surface chemistry. Ice exposed to radiation and ultraviolet light transforms over time. Darkening occurs. Surface layers evolve chemically. The radiation environment itself is unusual. Unlike Jupiter, which traps enormous radiation belts, Uranus's magnetosphere is tilted and offset. That means charged particles sweep across its moons in complex, time-varying patterns. Some regions may receive more bombardment than others. That radiation can alter surface chemistry, producing organic molecules and complex hydrocarbons. The moons of Uranus may therefore preserve records of magnetospheric history, frozen into their icy crusts. And yet, we know so little about them. Voyager 2's brief flyby provided our only close images. Since then, telescopes have improved, but resolution remains limited. We have not mapped these worlds in detail. We have not measured their internal structures. We have not sent landers or probes. The Uranian system remains one of the least explored regions of the solar system. And this neglect has consequences. Because planetary systems do not exist in isolation, the structure of a planet's satellite system reveals clues about its formation. For example, the orderly arrangement of Uranus's moons suggests they formed from a disk of debris, possibly after a catastrophic impact. If Uranus was indeed struck by a massive object early in its history, that impact could have created a disk of material around the tilted planet. From that disk, the current moons may have formed. In that sense, the moons may be second-generation objects, born from planetary trauma. This would parallel some theories about Earth's moon, which may have formed after a collision with a Mars-sized body. Planetary systems, it seems, are often born from violence, and Uranus may be one of the clearest examples. There is also the question of the small inner moons and rings. Uranus's ring system is narrow and dark. Shepherd moons maintain ring edges, keeping particles confined through gravitational interactions. But the rings are fragile. They may be relatively young. Collisions among small moons could replenish ring material. And over long timescales, gravitational interactions could reshape the entire system. The Uranian system is therefore dynamic, even if that dynamism unfolds slowly. Now zoom out. Imagine observing Uranus from far away, from another star system. It would appear as a pale blue exoplanet orbiting far from its host star. If its tilt were detectable, astronomers might note the extreme axial orientation. If its heat emission were measurable, they might find it unusually faint. If its moons transited the planet, their signals could reveal orbital patterns. In many ways, Uranus is a prototype for understanding ice giants in other systems. Exoplanet surveys have revealed that planets similar in size to Uranus, are among the most common in the galaxy. Yet we barely understand the two examples in our own system. This gap in knowledge becomes even more striking when we consider habitability studies. While Uranus itself is not habitable, its moons might harbor subsurface oceans, and beyond that, ice giants influence planetary system architecture. Their gravity can scatter comets and asteroids. They can shape the distribution of smaller bodies. They can alter orbital dynamics. Understanding Uranus is therefore essential for understanding planetary systems as a whole. But there is a psychological component as well. Uranus suffers from what could be called narrative neglect. It does not have rings as bright as Saturn's. It does not have storms as dramatic as Jupiter's. It does not have an obvious ocean world like Europa. Its name has been the subject of jokes for centuries, and so it drifts in the margins of popular imagination. Yet scientific importance does not correlate with entertainment value. Uranus forces us to confront our biases. We tend to focus on extremes, the biggest storms, the brightest rings, the most photogenic features. But planetary science often advances through subtle discrepancies, through anomalies in heat flow, through magnetic fields that do not align, through atmospheres that behave differently than expected. Uranus is full of such anomalies. Its heat emission is too low. Its magnetic field is too tilted. Its tilt is too extreme. Its moons are too strange. Each of these two statements signals an opportunity to refine our models, to question our assumptions, to expand our understanding of how planets evolve. And perhaps that is the deeper meaning behind calling Uranus misunderstood. It is not that scientists ignore it. It is that its quiet complexity demands patience. It demands missions that last decades. It demands instruments capable of probing deep into atmosphere and magnetosphere. It demands long-term observation. In an era of rapid discovery and headline-driven science, Uranus asks us to slow down, to commit to exploration for the sake of knowledge rather than spectacle. Because if we truly wish to understand planetary systems, including those far beyond our own, we cannot afford to leave the ice giants in the shadows. Uranus may not shine brightly in our night sky, but scientifically, it casts a long shadow across planetary science. And until we return to it, until we orbit it, probe it, map it, and measure it in detail, it will remain a planet that we see, but do not fully know. A world tilted on its side, quiet, distant, and still deeply misunderstood. There is one final layer to the mystery of Uranus that extends far beyond its atmosphere, its moons, or even its violent past. It is what Uranus represents in the larger story of planetary science. For centuries, the solar system seemed neatly organized. Small rocky planets close to the sun, large gas giants farther out, everything arranged in a pattern that felt almost intuitive. Then Uranus disrupted that simplicity. Discovered in 1781 by William Herschel, Uranus was the first planet found with a telescope. Until then, humanity had only known the planets visible to the naked eye. Its discovery expanded the known solar system overnight. But even that discovery carried confusion. Herschel initially believed he had found a comet. Its orbit later revealed it to be a planet, one that had been hiding in plain sight, faint and distant, overlooked for millennia. In many ways, that is symbolic. Uranus has always been there, quietly reshaping our understanding without demanding attention. Its discovery forced astronomers to reconsider the scale of the solar system. If one hidden planet could exist beyond Saturn, perhaps others could too. And indeed, irregularities in Uranus's orbit eventually led to the discovery of Neptune. Tiny deviations in its motion suggested the gravitational pull of another unseen planet. Mathematical prediction guided telescopes to Neptune in 1846. So even in its early history, Uranus served as a bridge between observation and theory, between mystery and calculation. But the deeper scientific impact of Uranus lies in how it challenges planetary classification itself. For much of the 20th century, Uranus and Neptune were grouped with Jupiter and Saturn as gas giants. But as measurements improved, scientists recognized that Uranus and Neptune are fundamentally different. Jupiter and Saturn are dominated by hydrogen and helium. Uranus and Neptune contain far more heavy elements: water, ammonia, methane. This led to the category of ice giants. But even that term oversimplifies. As laboratory experiments and theoretical models improved, researchers realized that the materials inside Uranus are not simple ices. Under extreme pressures, water behaves in unfamiliar ways. Methane may break apart into carbon structures. Hydrogen may exist in exotic phases. The deeper we probe, the more Uranus resists neat labels. It is not just a scaled-down Jupiter. It is not merely a colder version of Saturn. It is a fundamentally different kind of planet. And that difference matters enormously when we look beyond our solar system. Exoplanet discoveries over the past 3 decades have revealed that planets the size of Uranus are extremely common. In fact, many planetary systems appear dominated by worlds between Earth and Neptune in size. These sub-Neptunes, or mini-Neptunes, may share properties with Uranus: thick atmospheres, volatile rich interiors, complex magnetic fields. If we misunderstand Uranus, we misunderstand the most common planetary type in the galaxy. And that makes Uranus not just an overlooked planet, but a cornerstone of comparative planetology. There's also the question of atmospheric chemistry. Methane gives Uranus its blue-green color by absorbing red light. But deeper in the atmosphere, methane may break apart under high pressure, forming heavier hydrocarbons. Some models even suggest that carbon could crystallize into diamond-like structures. In 2017, laboratory experiments using high-powered lasers simulated conditions similar to those inside Uranus. The results suggested that diamond rain could occur, carbon atoms compressing into diamond structures that fall deeper into the planet. If true, Uranus may experience a slow rain of solid carbon within its interior, not the sparkling gems of Earth's jewelry stores, but dense crystalline carbon sinking through superionic layers. It sounds almost fantastical, but it emerges from physics, not imagination. This possibility reminds us that planetary interiors are not static. They are dynamic, evolving systems governed by extreme pressures and temperatures. And Uranus, with its suppressed heat flow and layered interior, may be uniquely suited for such exotic processes. Now consider the future of Uranus. Over billions of years, the Sun will evolve. It will expand into a red giant, dramatically increasing in size and brightness. When that happens, the outer solar system will warm. Moons of Uranus that are now frozen may thaw. Ices may melt. subsurface oceans could become surface seas. Temporarily, for a brief cosmic moment, regions that are now inhospitable could become more temperate. This long-term evolution highlights another lesson from Uranus. Planetary environments are not fixed, they change. Over millions and billions of years, worlds transform. Tilted axes, suppressed heat flows, hidden oceans. All of these factors influence how a planet responds to stellar evolution. And when we consider exoplanets orbiting different types of stars, these lessons become even more important. Planets around red dwarfs may experience tidal locking. Planets around hotter stars may endure intense radiation. The diversity of planetary systems in the galaxy likely includes countless worlds with unusual tilts, exotic magnetic fields, and layered interiors. Uranus serves as our local example of that diversity. But perhaps the most profound reason Uranus is misunderstood is philosophical. We tend to equate drama with importance. Jupiter's great red spot is dramatic. Saturn's rings are dramatic. Mars' potential for past life is dramatic. Uranus offers no such immediate spectacle. Its storms are subtle. Its rings are dark. Its magnetic field is invisible. Its interior mysteries are hidden beneath thousands of kilometers of atmosphere. Understanding Uranus requires patience. It requires models, laboratory experiments, decades-long observations. It requires accepting uncertainty. In that sense, Uranus represents the quieter side of science, not discovery through explosive events, but through persistent questioning, not through bright imagery, but through careful measurement. And maybe that is why it feels overlooked. In popular culture, Uranus is rarely featured. It does not dominate textbooks or documentaries. But among planetary scientists, interest in Uranus has been growing. The 2022 Planetary Science Decadal Survey identified a Uranus orbiter and probe mission as a top priority. That recommendation reflects recognition of how central Uranus is to unresolved questions in planetary science. A dedicated mission would not just study one planet. It would test theories of magnetic field generation. It would refine models of planetary formation. It would calibrate our understanding of ice giants in other star systems. It would investigate potential ocean worlds among its moons. In short, it would transform Uranus from a peripheral curiosity into a key to unlocking planetary diversity. And perhaps that transformation is already underway. The more we learn, the more we realize that Uranus's apparent simplicity is deceptive. Its low heat emission may mask layered convection. Its smooth appearance may conceal seasonal storms. Its unusual tilt may be a scar from ancient violence. Its magnetic field may be generated in a shell rather than a core. Its moons may hide subsurface oceans. Its interior may host superionic water and diamond precipitation. Each of these possibilities expands our view of what planets can be. And when we step back, we see a pattern. Uranus challenges assumptions. It challenges the idea that planets form neatly. It challenges the expectation that magnetic fields align with rotation axes. It challenges the notion that low heat emission means low activity. It challenges the idea that visual blandness implies physical simplicity. In a universe where diversity appears to be the rule rather than the exception, Uranus is a reminder that even within our own solar system, there are worlds we barely understand. And perhaps that is the ultimate meaning behind calling Uranus misunderstood. It is not misunderstood because scientists have ignored it. It is misunderstood because it defies easy explanation, because it does not fit comfortably into categories, because it sits at the edge of the solar system, of our knowledge, of our imagination, tilted, quiet, blue-green against the darkness, a planet that asks us to look deeper, think longer, and question more carefully. And until we return, until we send a spacecraft to orbit it and probe its depths, Uranus will remain a world we see clearly, but know only in fragments, a planet that appears simple from afar, but grows stranger the closer we look. There is something almost poetic about the way Uranus moves through space. While the other planets spin like tops, their axes tilted only slightly, Uranus rolls. It rotates like a barrel on its side, its north and south poles pointing almost directly at the Sun in turn as it completes its long 84-year orbit. That single detail, the 98-degree axial tilt, is often mentioned as a curiosity, a fun fact, an oddity. But it is far more than that. The tilt defines Uranus. It shapes its seasons, its atmosphere, its magnetosphere, its moons, and perhaps even its internal structure. To truly understand Uranus, we must stop thinking of it as a normal planet that happens to be sideways. It is a fundamentally different kind of world. Imagine standing on a hypothetical moon orbiting Uranus. For more than 2 decades, you would watch one hemisphere of the planet bask in continuous sunlight, while the other remained in darkness. The illuminated pole would glow faintly blue-green against the blackness of space. Then slowly, almost imperceptibly, the seasons would change. The sun would drift toward the equator. Light and shadow would redistribute, and the previously dark hemisphere would begin its long, slow sunrise. This is not a seasonal shift like Earth's. It is not spring melting into summer. It is a planetary scale rebalancing of energy that unfolds across generations. The implications of this are profound. For years, scientists assumed that Uranus's extreme tilt would produce massive atmospheric temperature differences between hemispheres. After all, one pole receives sunlight for decades, while the other receives almost none. But measurements show that the temperature distribution is surprisingly uniform. Why? The answer likely lies in atmospheric dynamics. Despite its low internal heat output, Uranus's atmosphere appears capable of redistributing solar energy across latitudes. Winds and circulation patterns move heat from illuminated regions to dark ones, but the mechanisms are not fully understood. The tilt also influences the magnetosphere in ways unlike any other planet. Because Uranus's magnetic field is already tilted relative to its rotation axis, and because the rotation axis is itself tilted relative to its orbit, the entire magnetic structure undergoes dramatic changes over time. As Uranus rotates, the magnetosphere wobbles. As Uranus orbits the Sun, the orientation of the magnetic field relative to the solar wind shifts dramatically. This creates complex interactions between charged particles and the planet's environment. Auroras on Uranus, for example, do not behave like those on Earth or Jupiter. They are offset. They appear in unexpected regions. They flicker in response to solar wind conditions in ways that are still being studied. Auroras are more than beautiful light displays. They are indicators of magnetic field structure and atmospheric composition. On Uranus, they offer clues about how the magnetic dynamo operates deep within the planet. And yet, Because we have only brief snapshots from Voyager 2 and distant telescope observations, our understanding remains incomplete. Now consider the gravitational implications of Uranus's tilt. When a planet is knocked onto its side by a massive impact, that collision does not simply change orientation. It redistributes angular momentum. It may alter the planet's internal layering. It may affect how moons form and evolve. If Uranus experienced a giant impact, the debris disk created by that event could have reaccreted into the current moon system. That would mean Uranus's moons are younger than the planet itself, second-generation objects born from catastrophe. And if that is true, then Uranus's tilt is not just a feature. It is a fossil record of violence. It tells a story of early solar system instability. The outer planets did not always sit peacefully in their current positions. Models of planetary migration suggest that Jupiter and Saturn may have moved significantly in the early solar system, altering gravitational relationships. Those shifts could have destabilized smaller bodies, triggering impacts across the outer regions. Uranus's tilt may therefore be part of a broader narrative of planetary reshuffling, a reminder that the solar system we see today is the product of chaotic evolution. There is also the psychological dimension. We often think of the solar system as orderly, planets orbiting in near-circular paths, rotating in predictable ways. Uranus disrupts that image. It rolls instead of spinning upright. Its poles take turns facing the sun directly. Its magnetic field behaves oddly. Its heat emission is anomalously low. It does not conform to expectations, and that non-conformity challenges us. Science advances when anomalies are investigated rather than ignored. If Uranus behaved exactly like Neptune, we might not question our models, but because it differs, despite similar size and composition, we are forced to ask deeper questions. Why does Neptune radiate significant internal heat while Uranus does not? Why is Neptune's atmosphere visibly dynamic while Uranus appears calmer? Are their internal structures fundamentally different? Did they experience different formation histories? Or are we misinterpreting limited data? Each of these questions feeds into broader themes in planetary science. Planetary formation is not a single pathway. There are multiple routes to building worlds. Some planets accrete smoothly. Others endure late-stage impacts. Some maintain convective interiors. Others become layered and stratified. Uranus may represent a class of planets shaped by suppressed convection, where compositional gradients inhibit heat transport. If that is the case, then many exoplanets in similar size ranges could behave the same way. That realization changes how we interpret exoplanet observations. When astronomers measure a planet's radius and mass, they infer density. From density, they infer composition. But if layered interiors trap heat differently, the radius of a planet could evolve in unexpected ways over time. Understanding Uranus is therefore essential for modeling planetary evolution across billions of years. Now let us consider something even more subtle: color. Uranus and Neptune are both blue due to methane absorption. But Uranus appears slightly paler. Recent studies suggest that differences in atmospheric haze layers account for that variation. Neptune may have more active vertical mixing, bringing methane and other compounds higher into the atmosphere. Uranus's calmer upper atmosphere may allow haze to accumulate differently. That difference in haze thickness affects light scattering. Such a seemingly small detail, a variation in shade, carries information about atmospheric dynamics, and it illustrates a key lesson. Planetary appearances are shaped by physical processes. Color is data, brightness is data, smoothness is data. Every visible feature reflects underlying physics. The smooth look of Uranus is not emptiness. It is a sign of subdued convection, of haze distribution, of methane chemistry, and perhaps of suppressed heat flow. When we combine all of these factors, tilt, magnetic field, suppressed heat emission, layered interior, unusual moon system, we see a coherent theme. Uranus is a planet shaped by imbalance, tilted orientation, offset magnetic field, uneven heat distribution, stratified interior, second-generation moons. Each imbalance tells a story. Each one suggests that planetary systems are not tidy machines. They are dynamic systems capable of producing worlds that defy expectations. And that is why Uranus matters so deeply to planetary science. It is not the brightest, it is not the largest, it is not the most visually dramatic, but it may be one of the most instructive, because it forces us to confront the limits of simple models. It forces us to admit what we do not know. And perhaps most importantly, it reminds us that our solar system still contains worlds that remain fundamentally mysterious. For decades, Uranus has drifted at the edge of attention. Yet the more we study it, the more it emerges as a keystone, a planet that bridges inner and outer system dynamics, a planet that challenges magnetic field theory, a planet that may hold clues about the most common planetary types in the galaxy. In the end, Uranus is not misunderstood because it lacks intrigue. It is misunderstood because its intrigue is quiet, subtle, hidden in data rather than spectacle. And until we return, until we orbit, probe, and observe it over long timescales, Uranus will continue to roll silently around the sun, sideways, blue-green against the dark, carrying answers to questions we are only beginning to ask. There is a final dimension to understanding Uranus that is rarely discussed, and it has less to do with physics and more to do with perspective. For most of human history, the outer solar system was a boundary of imagination. Beyond Saturn lay darkness. Uranus was invisible to the naked eye, faint and distant, blending with background stars. It existed in the sky long before its discovery, but without instruments, it was indistinguishable from countless points of light. When William Herschel first observed Uranus in 1781, he did not realize he had discovered a planet. He thought it was a comet. That mistake is telling. Uranus was not obvious. It did not announce itself as a world. It had to be measured, tracked, calculated, and reclassified. From the very beginning, Uranus challenged perception. Even today, it does. When we look at photographs of Uranus, we see a smooth sphere. No great bands, no dramatic storms visible to the naked eye. Compared to Jupiter or Saturn, it appears almost unfinished. But that is the trap of appearance. The human brain is wired to interpret contrast and motion. We see Jupiter's stripes and assume complexity. We see Saturn's rings and assume grandeur. Uranus offers neither spectacle nor dramatic contrast. And yet, beneath that calm exterior lies one of the most physically intriguing planets in the solar system. The misunderstanding of Uranus may stem partly from scale. It is enormous, about 4 times Earth's diameter, yet it feels small in comparison to Jupiter. It is distant, about 19 astronomical units from the Sun, yet not as remote as Neptune. It sits in a kind of psychological middle ground, too far to be familiar, too subtle to be sensational. But if we shift perspective, Uranus becomes extraordinary. Imagine shrinking the solar system down to the size of a city. Earth would be a tiny marble near the center. Jupiter would loom like a massive beach ball farther out. Uranus would be an immense sphere at the edge, tilted dramatically, rolling slowly around its orbit over 84 Earth years. Each season would last longer than a human generation. Children born during the start of Uranian summer would grow old before winter began. That timescale alone sets Uranus apart. It forces us to think beyond human lifetimes. Most of our planetary intuition is shaped by Earth. Daily rotation, yearly seasons, short-term weather patterns. Uranus operates on rhythms that dwarf human experience. Its axial tilt means that sunlight strikes it in a way no other planet experiences. At solstice, one pole points almost directly at the Sun. The equator lies in permanent twilight. The opposite pole is plunged into darkness for years. What does that do to atmospheric chemistry, to cloud formation, to energy transport? We do not yet know. But we suspect that Uranus's long-term seasonal transitions may trigger atmospheric responses that unfold over decades, because Voyager 2 visited Uranus near solstice in 1986. We saw it during a specific seasonal phase. As Uranus approached equinox in the 2000s, telescopes began detecting increased storm activity. That suggests the planet's atmosphere is far more dynamic during seasonal transitions than previously thought. We have not observed Uranus through a complete seasonal cycle since its discovery. No human has witnessed a full Uranian year. That fact alone underscores how incomplete our understanding is. Now consider the question of internal structure. Traditional planetary models assume that large planets cool over time, radiating internal heat left over from formation. Jupiter and Saturn still glow faintly in infrared, emitting more energy than they receive from the Sun. Neptune does the same. Uranus does not. It emits almost no excess heat. Why? One hypothesis suggests that the giant impact that tilted Uranus may have rearranged its internal layers in a way that suppresses convection. If heavy elements and lighter gases became stratified, heat transport could be inhibited. Imagine a layered fluid where denser material sits beneath lighter material in stable configuration. Convection becomes difficult. Heat becomes trapped. If Uranus's interior is layered like this, it may still contain substantial internal energy, but that energy is not efficiently escaping. That possibility changes how we interpret its thermal evolution. Perhaps Uranus is not cold because it formed differently. Perhaps it is cold because it was disrupted differently. And that distinction matters, because if impacts and layering can suppress convection in ice giants, then similar processes may operate in countless exoplanets. In recent years, laboratory experiments have simulated high-pressure conditions found inside Uranus. Scientists have recreated superionic water, a phase of matter where oxygen atoms form a rigid lattice while hydrogen ions move freely. If such material exists inside Uranus, it could explain the unusual magnetic field. Earth's magnetic field is generated by convection in a molten iron core. On Uranus, the magnetic field may originate in a shell of superionic water-ammonia mixture rather than a central core. That shell would produce a magnetic field offset from the center and tilted relative to the rotation axis, exactly what we observe. The magnetic field is not aligned, it is not centered, it behaves unpredictably as the planet rotates. For spacecraft traveling through the magnetosphere, that means variable radiation exposure. For the moons, it means charged particles sweep across surfaces in complex patterns. The offset magnetic field creates a magnetosphere unlike any other. This too has implications for exoplanets. If ice giants commonly generate magnetic fields in shells rather than cores, then our models of planetary magnetism need revision. Magnetic fields are critical for shielding atmospheres from stellar winds. Understanding how they form determines how we assess planetary habitability. Uranus, once dismissed as dull, suddenly becomes central to astrobiological considerations. And then there are the rings, dark, narrow, composed of radiation-processed material. Unlike Saturn's bright, icy rings, Uranus's rings are subtle and easily overlooked. They were discovered through stellar occultation, a technique that measures dips in starlight as a planet passes in front of a star. Before the planet blocked the star entirely, several small dips occurred. Rings. The discovery of Uranus's rings reminded scientists that planetary systems often surprise us. Even the quiet planet had hidden structure, and those rings are dynamic. Shepherd moons maintain their edges. Collisions among small bodies replenish material. Over long timescales, the ring system may evolve significantly. Perhaps rings are temporary features in planetary lifetimes. Perhaps Saturn's brilliant rings are the exception rather than the rule. Uranus's darker rings may represent a different evolutionary stage. Every aspect of Uranus invites deeper questions. Its tilt invites questions about planetary collisions. Its magnetic field invites questions about dynamo mechanisms. Its low heat emission invites questions about interior layering. Its moons invite questions about ocean worlds. Its rings invite questions about debris disk evolution. And yet, we have only visited it once. One flyby, a few hours of data, no orbiter, no atmospheric probe. In contrast, Jupiter and Saturn have hosted multiple missions. Mars has been explored by rovers and orbiters for decades. Even Pluto, once considered marginal, was visited by New Horizons. Uranus remains largely unexplored. That neglect is beginning to change. Planetary scientists increasingly advocate for a Uranus orbiter and probe mission. Such a mission would transform our understanding. An orbiter could map the gravitational field in detail, revealing internal mass distribution. A probe could descend into the atmosphere, measuring composition directly. Long-term monitoring could capture seasonal evolution. Magnetometers could map field variations over time. For the first time, Uranus would be studied as thoroughly as Jupiter or Saturn. And perhaps then, the label of misunderstood would fade, because misunderstanding does not arise from ignorance alone. It arises from incomplete narratives. We have told a simple story about Uranus, a cold, sideways planet at the edge of the solar system. But the real story is far richer. A planet shaped by ancient impact, a world with layered interior and exotic phases of matter, a magnetosphere unlike any other, moons that may hide subsurface oceans, seasons that span decades, rings that whisper of past collisions. Uranus is not an afterthought. It is a frontier. And until we explore it fully, it will remain not a joke, not a footnote, but a reminder that even in our own cosmic neighborhood, there are worlds we barely understand, sideways, silent, still waiting. If we are honest, the reason Uranus feels misunderstood is not because it lacks data alone. It is because it forces us to confront how much of planetary science is built on comparison. We understand Jupiter because we see its storms. We understand Saturn because we studied its rings for decades. We understand Mars because we walked on it through machines. But Uranus sits between familiarity and mystery. It is close enough to observe, yet far enough to avoid deep exploration, large enough to matter, yet subtle enough to be overlooked. And that position has shaped how we think about it. For decades, Uranus was treated as a quieter twin of Neptune, similar size, similar mass, similar composition, similar blue color. But twins are rarely identical. And when scientists began comparing detailed measurements, inconsistencies emerged. Neptune radiates significant internal heat. Uranus does not. Neptune displays dramatic storms regularly. Uranus shows activity mostly during seasonal shifts. Neptune's atmosphere appears more dynamically mixed. Uranus seems more stratified. Two similar planets, two different outcomes. That difference tells us something critical. Planetary evolution is sensitive to history. Small changes early in formation can lead to radically different long-term behavior. Imagine two planets forming side by side in the protoplanetary disk. One experiences a massive collision, the other does not. Billions of years later, one planet may have suppressed convection, a tilted axis, and altered interior layering. The other may radiate heat normally and exhibit stronger atmospheric mixing. That is not a minor detail. It is a reminder that planetary systems are chaotic. There is no single template for how a world must behave, and that insight reshapes our interpretation of exoplanets. When astronomers detect a Neptune-sized world orbiting a distant star, they measure its mass and radius. From those two numbers, they infer density. From density, they model interior composition. But what if two planets with identical mass and radius have radically different internal histories? What if one has a layered interior that traps heat and the other has efficient convection? They may appear similar in bulk measurements, yet behave differently in magnetic activity, atmospheric evolution, and long-term cooling. Uranus teaches us caution. Surface similarity does not guarantee internal similarity. Now consider something even more fundamental: rotation. On Earth, rotation shapes climate. It determines day and night cycles, influences atmospheric circulation, and drives weather patterns. On Uranus, rotation operates in a different geometric framework. Because its axis is nearly parallel to its orbital plane, sunlight distribution changes dramatically over time. At solstice, the sun hovers almost overhead at one pole, while the equator receives limited direct illumination. At equinox, sunlight strikes more evenly across latitudes. These long-term changes alter temperature gradients. Temperature gradients drive winds. Winds shape clouds. Clouds influence radiative balance. Radiative balance influences chemistry. In other words, Uranus's extreme tilt cascades through multiple physical processes. But because each stage unfolds slowly over decades, capturing the full picture requires patience. We have not yet observed a complete seasonal cycle with modern instruments. We are studying a slow symphony by listening to only a few notes. And yet, even with limited data, surprises continue. In recent years, astronomers observed unexpected brightness changes in Uranus's polar regions. As one pole entered prolonged sunlight, cloud formation increased. Bright polar caps appeared. These changes were not anticipated by early models. They forced scientists to revise assumptions about methane condensation and atmospheric mixing. Each new observation adds nuance. And nuance is what makes Uranus scientifically rich. Then there is the question of density. Uranus is less dense than Earth, but denser than Saturn. Its composition likely includes a mixture of hydrogen, helium, water, ammonia, and methane. But how these components are arranged remains uncertain. Is there a distinct core? Is the mantle homogeneous? Are there compositional gradients that prevent convection? Gravity measurements from an orbiter could answer these questions. Precise mapping of the gravitational field would reveal how mass is distributed inside the planet. Small variations in gravity can indicate internal layering. Without such data, we rely on indirect modeling, and models, while powerful, depend on assumptions. One particularly intriguing possibility is that Uranus contains a large fraction of heavy elements relative to hydrogen and helium. If so, it may represent a class of planets that are treated differently than Jupiter and Saturn. Perhaps Uranus formed later, when less gas remained in the protoplanetary disk. Perhaps it migrated from a different region. Perhaps it accumulated more ices and fewer light gases. Each scenario affects how we interpret planet formation beyond our solar system. If Uranus formed differently from Neptune, that difference might explain their divergent heat outputs. Or perhaps both formed similarly, but one experienced a transformative impact. The distinction matters, because in planetary science, formation history determines destiny. Even small early differences amplify over billions of years, and that amplification may explain why Uranus appears subdued while Neptune remains active. Now step back even further. Imagine an alien civilization observing our solar system from afar. They detect a star similar to the Sun. They detect multiple planets. Two of those planets are roughly similar in size and mass, orbiting at comparable distances. One radiates heat and shows atmospheric variability. The other appears colder and more stable. Without direct exploration, they would struggle to explain the discrepancy. They would build models, debate formation scenarios, speculate about impacts. In many ways, we are that alien civilization, trying to decode distant worlds with limited information. Except in this case, the world is only 19 astronomical units away, close in cosmic terms, yet distant enough to remain mysterious. This duality, proximity, and ignorance defines Uranus. We have sent probes beyond it. Voyager 2 flew past on its way to Neptune and interstellar space, and yet we have never lingered, never orbited, never descended into its atmosphere. The cost and complexity of a mission to Uranus are substantial. Travel time alone would span more than a decade. Power generation so far from the Sun requires radioisotope systems. Communications delays stretch into hours. But the scientific return could be transformative, because Uranus sits at the intersection of multiple disciplines: planetary formation, magnetospheric physics, atmospheric dynamics, exoplanet comparison, ocean world potential. Few planets touch so many fields simultaneously, and yet it remains quiet, understated, often reduced to a single joke in popular culture. That cultural trivialization may contribute to scientific neglect in public imagination. But within the scientific community, recognition is growing. Uranus is not a footnote. It is a laboratory, a natural experiment in planetary diversity. And perhaps its most important lesson is humility. We often assume that the largest planets, Jupiter and Saturn, dominate our understanding of gas and ice giants. But Uranus reminds us that scale is not the only measure of importance. Subtle differences can carry enormous implications. A suppressed heat flux can reshape atmospheric behavior. An offset magnetic field can redefine dynamo theory. A sideways axis can transform seasonal physics. A quiet exterior can conceal exotic interior states. In that sense, Uranus is not misunderstood because it is obscure. It is misunderstood because it challenges our expectations. It refuses to conform to the tidy patterns we prefer. It exists slightly outside the categories we constructed, and in doing so, it expands those categories. Planetary science is not just about cataloging worlds. It is about understanding processes, how heat moves, how magnetic fields form, how atmospheres evolve, how impacts reshape destiny. Uranus touches each of these processes, and until we explore it deeply, our understanding of them remains incomplete. It is easy to overlook a pale blue planet in the outer darkness, but sometimes the worlds that whisper hold more secrets than those that shout. Uranus does not demand attention. It invites investigation. And the more carefully we listen, the more it reveals that it is not a simple ice giant, not a sideways anomaly, but a key piece of the planetary puzzle. One that, once fully understood, may change how we see not just one planet, but thousands across the galaxy. If Uranus teaches us anything, it is that the solar system is not finished teaching us lessons. For a long time, planetary science was built around a simple hierarchy. The inner rocky worlds were active and complex. The giant gas planets were massive and dramatic. The outer ice giants were quieter, colder, less interesting. But that hierarchy was based more on visibility than reality. Jupiter demands attention. Saturn commands admiration. Even Neptune dazzles with visible storms. Uranus does not, and so it slipped into the background. Yet when scientists look carefully, when they stop expecting spectacle and start measuring subtleties, Uranus becomes one of the most revealing planets in the solar system. There is something almost paradoxical about it. It appears smooth, yet its winds are fast. It emits little heat, yet storms still erupt. Its magnetic field is chaotic, yet stable enough to persist. Its tilt is extreme, yet its orbit is nearly circular. Each contradiction forces us to refine what we mean by normal. In planetary science, we often use Earth as the reference point. It is the world we understand best. It defines our intuition about seasons, atmospheres, magnetic fields, and internal heat. But Uranus is a reminder that Earth-like expectations do not scale cleanly to larger or more distant worlds. On Earth, axial tilt of 23.5 degrees produces moderate seasonal change. On Uranus, a tilt of 98 degrees creates planetary-scale illumination shifts that last decades. On Earth, the magnetic field is generated in a central molten iron core. On Uranus, the magnetic field likely originates in a shell of superionic fluid, offset, tilted, and asymmetric. On Earth, Heat escapes through convection in the mantle. On Uranus, convection may be suppressed by compositional layering. Every process we understand locally becomes more complex when scaled up, and that complexity is precisely what makes Uranus valuable. Now consider the long-term evolution of ice giants. Over billions of years, planets cool. They radiate away the energy left over from formation. As they cool, internal dynamics slow, atmospheres evolve, magnetic fields may weaken. If Uranus's interior is stratified with layers that prevent efficient heat transport, its cooling history may differ significantly from Neptune's. Neptune may still convect vigorously, releasing heat and driving storms. Uranus may cool differently, trapping energy beneath stable layers. If that is true, then Uranus represents a different evolutionary pathway. Two similar planets, two divergent thermal histories, and that divergence could be common across the galaxy. Exoplanet surveys have revealed a surprising diversity in planet sizes and compositions. Many worlds are intermediate between Earth and Neptune in size. Some have thick atmospheres, some appear inflated, others are denser than expected. Without a detailed understanding of our own ice giants, interpreting these distant worlds becomes guesswork. Uranus serves as the calibration point. It is the example we can test if we choose to explore it fully. There is also the question of stability. Despite its dramatic tilt, Uranus's orbit is remarkably stable. It does not wander wildly. Its path around the Sun is nearly circular. That stability suggests that whatever impact or interaction altered its axis did not destabilize its orbit. In other words, planetary systems can absorb extreme events without collapsing. That resilience is important. It suggests that catastrophic impacts do not necessarily destroy planetary architecture. They reshape it. The solar system's current configuration, with Uranus rolling sideways in a stable orbit, is evidence of long-term gravitational harmony emerging from early chaos. This balance between violence and stability is central to planetary formation. Early solar systems are turbulent. Planets migrate, objects collide, debris disks form. But over time, systems settle, orbits stabilize, heat dissipates, atmospheres evolve. Uranus embodies that history. Its tilt whispers of ancient collision. Its subdued heat hints at interior rearrangement. Its orderly moon system suggests reformation after disruption. It is both survivor and witness. There is something else that makes Uranus scientifically profound. It challenges anthropocentrism in subtle ways. We often frame planetary exploration around the search for life. Mars is exciting because it may have once been habitable. Europa and Enceladus fascinate us because they may harbor oceans beneath ice. Uranus, by contrast, is not a candidate for life as we know it. Its atmosphere is hostile, its pressures immense, its temperatures extreme, but its moons may contain oceans. Titania and Oberon, the largest moons, are large enough that tidal heating or radioactive decay could have sustained internal warmth in the past. If subsurface oceans exist, even frozen worlds in the outer darkness may have been, or still be, chemically active. That possibility broadens the concept of habitable environments. Life may not require surface sunlight. It may persist beneath ice, shielded from radiation. Understanding Uranus's moons therefore contributes indirectly to astrobiology. And that connection reframes the planet once again, not as a sterile ice giant, but as the center of a system with potential for hidden complexity. The final layer of misunderstanding surrounding Uranus may be cultural. It has been reduced to a punchline. Its name, derived from the Greek sky god, has become a source of humor in English. That trivialization has subtly influenced public perception. It feels less majestic than Saturn, less intimidating than Jupiter, less romantic than Mars. But scientific significance does not depend on branding. Uranus does not need to be dramatic to be important. In fact, its quiet complexity may be more instructive than spectacle, because it teaches patience. It teaches the value of long-term observation. It teaches that first impressions can be deceptive. It teaches that subtle anomalies can reshape theory. In planetary science, revolutions often begin with small discrepancies. Mercury's orbit did not match Newtonian predictions, leading eventually to general relativity. Uranus's orbit deviated slightly, leading to the discovery of Neptune. If Uranus's heat emission does not match models, perhaps our understanding of convection in ice giants needs revision. If its magnetic field defies alignment expectations, perhaps dynamo theory must expand. Each anomaly is an invitation to question, to measure more carefully, to build better instruments, to return. And that may be the most important conclusion of all. Uranus is not misunderstood because it is simple. It is misunderstood because it demands a level of attention we have not yet given it. We have skimmed its surface. We have modeled its interior. We have observed it through telescopes, but we have not lived with it. We have not watched its seasons unfold from orbit. We have not sampled its atmosphere directly. We have not mapped its gravitational field in high resolution. The story of Uranus is incomplete, and that incompleteness is not a weakness. It is an opportunity to deepen our understanding of planetary diversity, to test formation theories, to refine magnetic field models, to compare ice giants across star systems. In the end, Uranus is not just a planet. It is a reminder that the universe does not conform to our expectations, that even within our own solar system, there are worlds that resist easy categorization. That complexity often hides behind calm appearances, and that sometimes the most misunderstood objects are the ones quietly holding answers to questions we have not yet learned how to ask. Sideways, blue-green, still rolling through the darkness, still waiting. In the end, the story of Uranus is not about strangeness alone. It is about perspective. For centuries, humanity looked up at the sky and saw 5 wandering stars: Mercury, Venus, Mars, Jupiter, and Saturn. Beyond Saturn lay nothing that the eye could distinguish. The solar system seemed compact, bounded, almost complete. Then Uranus was discovered, and with it, the boundary expanded. But expansion alone does not guarantee understanding. Uranus entered our maps, our textbooks, our diagrams, yet it never truly entered our imagination in the same way as other worlds. It became a distant sphere in a chart, a pale blue disk in a telescope image, a brief chapter in a planetary overview. And perhaps that is why it remains misunderstood. Not because it is obscure, not because scientists ignore it, but because it demands a kind of thinking that is slower, deeper, and less dramatic. Uranus does not offer volcanoes erupting into space like Io. It does not display rings glittering brightly like Saturn. It does not flaunt storms as visually obvious as Jupiter's great red spot. Instead, it asks quieter questions. Why does it emit so little heat? Why is its magnetic field tilted and offset? Why does its atmosphere appear calm, yet produce high-speed winds? Why does its twin, Neptune, behave so differently? Each question leads to another, and together, they reshape how we think about planetary systems. Perhaps the most important lesson Uranus teaches us is that similarity does not equal sameness. Neptune is similar in size and composition, yet it radiates heat strongly and displays constant storm activity. Uranus, nearly its twin in mass, behaves differently. That divergence reminds us that planetary outcomes are sensitive to initial conditions, a collision billions of years ago, a difference in accretion timing, a variation in internal mixing. Small differences early in formation can cascade into major differences billions of years later. This is not just about Uranus. It is about the entire universe of planets. When astronomers discover exoplanets, they categorize them by size and mass. They speak of super-Earths, mini-Neptunes, and gas giants. But Uranus warns us that categories are approximations. Two planets with similar measurements may have radically different internal structures and histories. And if that is true, then our galaxy is likely filled with worlds that defy easy classification. Uranus becomes a bridge between observation and humility. It tells us, do not assume too quickly. Now imagine the future. Imagine a spacecraft arriving at Uranus after a decade-long journey through deep space. It slows into orbit. Instruments deploy. Cameras capture detailed images of clouds, storms, and ring structures. A probe detaches and descends into the atmosphere. It measures methane abundance precisely. It samples hydrogen and helium ratios. It detects trace elements that reveal formation history. Magnetometers map the magnetic field in full three-dimensional detail over years. Gravitational measurements reveal whether the interior is layered or mixed. For the first time, Uranus would not be an approximation. It would be a world fully studied. What might we discover? Perhaps the heat suppression theory will be confirmed, layered convection trapping energy deep inside. Perhaps we will find that Uranus still contains significant internal heat, but releases it unevenly. Perhaps we will detect unexpected atmospheric chemistry. Perhaps one of its moons will show signs of subsurface ocean interaction. Each possibility expands our understanding. And that is what makes Uranus so essential. It is not simply another planet in the lineup. It is a test case for planetary diversity. It forces us to think beyond Earth-centered models. It forces us to recognize that planets can rotate sideways and still maintain stability, that magnetic fields can emerge from shells rather than cores, that calm appearances can mask complex interiors. There is something almost symbolic about Uranus's sideways posture. It is a planet that does not stand upright like the others. It rolls. It orients itself differently relative to the Sun. It challenges our visual expectation of what a planet should look like. And in that challenge lies a deeper truth. The universe is not obligated to conform to our preferences. It does not produce worlds that match our aesthetic sense of order. It produces variety, sometimes extreme variety. Uranus, in its quiet way, embodies that truth. It is neither the most massive nor the most luminous, but it is uniquely configured, uniquely structured, uniquely tilted. And that uniqueness is not trivial. It is informative. It tells us that planetary systems are shaped by events we may never directly observe, that impacts leave scars billions of years later, that internal processes can diverge even among similar worlds, and perhaps most importantly, it reminds us that our solar system still contains frontiers. It is tempting to believe that the age of discovery within our own planetary neighborhood is over. We have sent probes to Jupiter, Saturn, Neptune, Pluto. We have rovers on Mars. We have mapped moons and rings, but Uranus remains largely untouched. One flyby, a handful of distant telescope observations, a planet waiting for closer examination. And waiting does not mean stagnant. As we refine telescope technology and improve simulation models, Uranus continues to challenge assumptions. Infrared observations reveal atmospheric changes over time. Magnetospheric data hint at complex dynamics. Laboratory experiments simulate supersonic phases that may exist inside. Every year, the picture sharpens slightly. But until we return, it will remain incomplete. And that incompleteness is not a flaw. It is an invitation to explore not just for spectacle, but for understanding. Because in the grand narrative of planetary science, Uranus represents something profound. It represents the worlds that are not dramatic enough to dominate headlines, yet complex enough to transform theory. It represents the subtle anomalies that push science forward. It represents the reminder that even familiar star systems contain mysteries. When we look at Uranus through a telescope, we see a small, pale disk. But when we look at Uranus through the lens of physics, chemistry, and planetary formation, we see a laboratory, a world that may hold answers about how common planets form, cool, magnetize, and evolve. A world that teaches us caution in categorization. A world that encourages patience in exploration. In the end, Uranus is not misunderstood because it is obscure. It is misunderstood because it does not fit neatly into our expectations. And perhaps that is its greatest contribution. It forces us to expand those expectations, to imagine planetary systems not as orderly diagrams, but as dynamic histories, to see the outer solar system not as static, but as evolving, to recognize that even a quiet blue-green sphere rolling through the darkness can reshape how we understand worlds across the galaxy. Uranus is not a joke. It is not an afterthought. It is not simply a sideways anomaly. It is a planet that reminds us that the universe is richer, stranger, and more diverse than first impressions suggest. And until we stand, or rather orbit, beside it once more, it will remain what it has always been, a distant, tilted world, still rolling, still revealing, still misunderstood.